Today's all about understanding phase, how that affects subwoofer placement, and thus power alleys and valleys when we start to pull them apart. We're actually going to be walking through content from my upcoming course that's going to be dropping here very soon, and I'm excited to share it with you. And what I'm going to share with you first is actually some feedback from some beta testers who have been going through the course. They've completed it, and this is what they had to say. So I asked them at the end, what was your biggest aha or learning moment from this course? And one student said the biggest learning moment was a better understanding of phase. I knew what the slopes on a phase graph meant, but never could really connect the dots. Your explanation was fantastic. It helped me to best understand. And then another student said their biggest aha learning moment was how subwoofer offset affects phase relation and propagation at different frequencies. So that's exactly what we're going to unpack today. Some phase basics and how does that affect your subwoofers. If you're new to my channel, I've got a gift for you. It's my Audio Math Survival spreadsheet. And I've got that here at the link below or at producedbymkc.com/audio toolkit. I feel like to have a great results out of your sound system, if you want to get a measurement microphone and start tuning, or even design great rigs, having an understanding of the physics at hand that are under everything is what my course covers, but a lot of the calculations are here in the spreadsheet. So make sure and snag that. That will also put you on my email list so you can make sure and get an announcement when the course drops here very soon. All right, so let's jump right in. I've got the slides here, and we'll kick off a little bit into the phase segment. We're not going to go through the entire phase segment, but just enough to see what we can get out of our subwoofers. So phase describes where a certain frequency is in its cycle in degrees. This is from Michael Lawrence from his book. Make sure and check that out. It's Between the Lines, System Design and Alignment, something like that. Sorry, I don't remember the title, but anyway, definitely check out his book if you want to learn more about sound system design. I think that was a great, really succinct title or way to talk about phase. So phase compares where it's at in its cycle to a starting point, 0 degrees. And there's 360 degrees in a full phase cycle. I know 7th grade science is kind of coming back to you now. Let's start to step through and unpack what that means. So this is a great graphic from Jack Shadler. He has a free website that walks you through digital sampling theorem and how waveforms are sampled and what aliasing is and Euler's formula and all that. It's great. So just put in Jack Shadler circles, sines, and waves into Google and it'll come up. It's fantastic. So we can see right here that we have 0 degrees as our starting point right now, and we move now around the circle, and the amplitude of a perfect sine wave starts to get drawn. So this is a perfect sine wave. It is a regular movement throughout the phase wheel from 0 to 360 degrees. So if we slow that down, here at 0 degrees or almost 0 degrees is where we start, and that is right here. And to go from this resting point going through a complete cycle, that is one full wavelength. And every frequency is gonna go around its phase cycle at a different speed, thus giving us a different wavelength. So we'll look at that relationship soon. So that's 0 degrees. Then we go to here at 90 degrees, and that is a quarter wavelength. And that's the maximum amplitude is at a quarter way through. Then we get to 180 degrees. Now we've started at resting, and now we're up to maximum. We've now come back down to resting, and we're gonna draw the mirror image on the negative half of the waveform. The positive half is up here, and negative will be below. So it's an even half and half for a sine wave at least. Now we're around to 270 degrees, and that's 3/4 wavelength. And now we have made a full lap. We've gone around, and we've now gone from resting up, down here, and now we're at 1 wavelength. So that's a complete 360 degrees at a given frequency. We don't know what frequency this is, but we know we have completed 1 wavelength. So phase, if you see what's going on here, it works a lot like a clock. In time telling, midnight or noon are helpful 0 points. So here in America, we use 2 12-hour blocks. I know in other parts of the world, it's a 24-hour clock. So if we were to ask here, what time is it here on this clock on the picture? It is 1:02 p.m. Easy, right? It is 62 minutes past noon. That's another way to say that. Noon is our 0 point, and now it's 1 hour and 2 minutes, or 62 total minutes. It's also 2 minutes past 1 p.m. So there's just lots of different ways to describe what time is it. So 1:02 p.m. is 1 hour or lap around. So the minute hand went one time around, and then the hour hand is keeping track of how many times it went around. So a 1 hour lap plus 2 minutes. That means the minutes resets our hours. And the same thing goes with phase. So 540 degrees would be 360 degrees 1 lap plus 180, which is another half lap. So that is 1.5 laps around. All right. We can also compare the phase relationship between two different frequencies. So let's watch a race. So frequency A, frequency B. So they are both at the starting line. So the red and blue little bricks right there are my poor attempt at a race car. So red now has a quarter lap or a 90-degree lead on the blue car. Now the blue car's taken off and it's lagging 90 degrees. The race keeps going. Red is ahead by 90 degrees. And so red stayed 90 degrees ahead for the duration of the race, all right? Now let's start combining waves. What about two sound waves with the same single frequency combining together at different points in their phase cycles? And we'll also clarify here, let's make it equal amplitude, so it's equal strength levels as well. So if we look at this phenomenal graphic from Merlin Van Veen, we'll see some of his resources here later on as well. He's a phase genius. So what we have here on the right-hand side is the simplified phase wheel. When we jump over to the left-hand side, if we have two waves coming together, they're exact copies of one another that are completely phase aligned, there's no phase offset between them, we get a perfect 6 dB doubling. So it's the same sound coming together at the same time, they double, and that's expressed from a voltage or sound pressure level standpoint by plus 6 dB. As we move around the phase wheel, we get further and further offset, and now we meet kind of the stalemate point of 0 degrees. So let's actually draw it around to the right. Right here is 0 dB, and this corresponds with a 120 degree offset. So we can move a third of the way, because 120 degrees is a third of 360 way through the phase cycle, and now we are at our stalemate. So I can have two exact waves, they come together, 120 degrees offset, we're actually just going to get equal to one of those waves again. So it's a 0 dB, no summation, no attenuation. Sorry, couldn't find that word. But if we keep moving around here and we get completely out of phase or 180 degrees offset, we get complete and total cancellation. So we have this gradient in between also. So it's plus 6 dB, we go here to 90 degrees, you get 3 dB, then it's stalemate, some cancellation, and now complete and total cancellation. So it depends, the phase relationship between two different frequencies or two different waves will determine whether they sum together, stay the same, or get reduced. So let's look at this in action. So this is another resource from Merlin Van Veen. You can Google him and find his calculators page on his website, and it has all of this. So definitely check that out. So this is two waves exactly in phase. When they sum together, they double in amplitude. So the legend is right here, is that our green line, which is covered up by the blue line right now, so it's the A wave and the B wave. The B wave is overlaid on the A, we can't see it, but that sums together to get us a doubling, because this was here to 1 being its positive amplitude, and now it doubles to 2 when they combine together. All right, so two equal waves in both amplitude and phase relationship combined together, it's the same as 1 plus 1 equals 2. So two waves 180 degrees out of phase sum together for complete cancellation. So here is our A wave going to positive 1, negative 1. So if you add positive 1 and negative 1 together, you're going to get this line right here, which is a summation, and that's cancellation. So they're going to cancel each other out. So two opposite polarity waves combining, that means 1 minus 1 equals 0. Let's look at in between. So two waves 90 degrees offset sum together and they get some addition. So we don't get a cancellation, we don't get our full 6 dB, we get 3 dB. And we can see these here that they are offset by 90 degrees. This entire graph here is 4 equal segments of 90 degrees. So we're looking at here and here and here. And we can see that this wave, the crest of the green one versus the crest of the blue is 9 degrees apart. And now they sum together to give us a 3 dB addition, or a 40% increase. If we look at these waves, were both at 1, and now increasing from here, it's almost halfway to the 2, so that's a 40% increase. So A plus B with the 90 degree offset between those two waves gives us a 40% increase. So a wave plus a 90 degree offset copy of that wave, 1 plus 0.4 equals 1.4. One more. So what about two waves that are 151 degrees offset? They sum together to get some loss. So if we look at the difference here between wave 1, it peaks right here at 90 degrees, so we draw this line, and it now is here. We see 90 degrees to 151 degrees offset. That is our addition right here, or actually subtraction. We from the two original ones, they come together and we get some loss right here. And you can see it's pretty cool that the resulting wave just kind of finds the middle point here and creates a new wave. So a wave plus 150 degree offset copy of that wave, 1 minus 0.5 equals 0.5. So what? Okay, let's look at this, how it actually applies to subwoofers now. Now we're in map 3D and we're looking at a top-down view at a single subwoofer. The frequency we have in mind right now is 100 Hertz. If we go over here to my Audio Math Survival spreadsheet, we can see that 100 Hertz, if we type that in here at the top, that tells us it has a wavelength of 11.3 feet. So for it to have its waveform going up and down, back to negative, up and down, I'm sorry, this is a sawtooth wave and not a complete sine, but the time it takes to go through its complete cycle is going to travel 11.3 feet, and it's going to take 10 milliseconds to do so. All right, so 11.3 feet, let's remember that number. So back here in map 3D, I've drawn a circle around this, which is 11.3 feet radius. So from here to here, 11.3. So we could see after it radiates out spherically from that point, it's going to start a new phase cycle. So that's what that pink circle is doing for us. So if I hit predict, here's our SPL map, and it has a slight forward leaning in the response. It's not a complete perfect circle. If we went down to 50 Hertz, it would basically be a perfect circle, but I just want to show you that a single sub is omnidirectional. It's going to radiate equally out in all directions. Now, what about if we have two subs? So now I'm placing these two subs, and we can see their Venn diagram is a little bit split apart now, a quarter wavelength apart from each other. So that's 11.3 feet divided by 4, so they are 2.82 feet apart. Now let's look at 100 Hertz. We have now narrowed our coverage. It feels counterintuitive, but the more we pull elements apart up to a complete wavelength, or half wavelength, we're going to start to narrow the pattern. And we'll talk a little bit later why that is. So let's keep widening it out. How about a half wavelength? Hit predict. And now it's very, very narrow. We've kind of squished this down into a figure 8 pattern. This is really similar if you think about an omnidirectional microphone, a cardioid microphone, and then on a figure 8. So in between omnidirectional is the other end is figure 8, and then we kind of have a blend of cardioid in the middle. So it's cool to see how speakers and microphones are mirror images of each other. So a half wavelength. Let's zoom in a little bit and start to think about why are we seeing this type of response. So if this is a half wavelength away from the center of this sub to get to the center of this sub, so that's 11.3 divided by 2, so 5.65, call that 5.5 feet is what's happening there. That means that we are now a half wavelength apart. So if we go back to this part, the presentation, this is what we are seeing. We are seeing now these two waves, when they arrive at that point, are now canceling each other out as they're moving north and south in this direction. So that's why we have not much sound going this way, but they are summing this way, because when we have them arrive here and here, they are at the same point in their phase cycle. So they sum together perfectly, and they are gradually offset in time as we move off over this way, And then by the time they're moving here and here, they maintain that half wavelength spacing in time and they cancel each other out. So if you want to make your sub coverage as skinny and narrow, maybe you're in a venue that's really skinny and long, I would pull apart your subs to a half wavelength of the highest frequency they're going to produce. So I would maybe go a third of an octave above your crossover. So it actually probably go to 125 to look at that a little bit better. So with this spacing, things start to get weird and we get side lobes. But let's go back to 100 and now look at 2/3 wavelength spacing. Now, since we've gone beyond half wavelength, we're now around the other side of the phase wheel right here, and we're starting to get some addition. So what's happened here, going back to our graphic, we have the phase wheel here, and we've gone from, they were right together, 0 degrees, now is a half wavelength spacing, and now we've moved out to the other side of 2/3 wavelength, and now we're getting some addition on the other side. So we're both getting sound moving out towards our audience, and if I didn't clarify earlier, I'm assuming our audience is out to the right here, because most are drawn that way. So we're getting some out here, but most of it is still going this way. Now let's move it a complete and full wavelength apart. And now we have more energy going to the sides because we measure from here to here. It's gone through a full cycle and now it's back at 0 and it's going to sum together and go that way. So we have more going north and south, which is where we don't want it, than east and west. They're still meeting here in the middle at equal level and phase, so they're summing that way, but we still have this clover leaf of these power valleys. So that's where we get power alleys and valleys from, is by pulling apart low frequency sources. This also happens at higher frequencies, but at a much higher rate. So let's look at that at 3 wavelengths, just to pull them far apart. So right now they are 11.3 times 3, 33 feet apart, which is not uncommon to have maybe a 32-foot wide stage. That's a medium-sized stage, so this is not common to have our subs that far apart if we're forced to do left-right. So again, we're looking at 100 hertz, and now we have this pattern. Again, we have more energy moving off to our side lobes because at their perfect 3rd wavelength spacing, so they're going through 3 complete cycles and bam, summing together. And then we have these nice little rivers of blue, as Bob McCarthy likes to call them, radiating through to our audience. And this is also a different pattern at every frequency because they have a different wavelength. So we move down to 50 hertz, let's hit predict, have the same thing. So it's not consistent at every frequency. So as you move left to right through your audience, you're going to hear this alternating of like 50 hertz is hot and 100 hertz is low, and now 100 hertz is hot and 50 hertz is low. So back at 100 hertz, let's actually measure and verify that this would be happening in the real world. So it's pretty tiny here in Map 3D, but I placed a microphone right here and I can measure to it. So let me use the measure tool. I'm going to go from the top corner of this sub, measure to right here, and that is 41.71 feet. So 41.74, let's write that down. Back to map. Here we are, outside corner of this sub, going to measure to right here, and that is 47.08. And just so you can see the prediction, I on purpose, have to exit out here, it looks like. I put it right here on purpose in the middle of a power valley. So power alley is where it sums together, and a power valley is where we get complete cancellation. So it's right here. So let's look at that distance offset. So let's do 47.08 minus 41.74, and that is 5.34 feet. So we should be able to double that, 5.34 times 2, and get back to a full wavelength. So that means it's a half wavelength, and we are at 10.68 feet, which is really close to 11.3. So this isn't me measuring from the outer corners, maybe made it a little bit less accurate, but Map 3D doesn't let me measure from the center of the sub, just the corners. Anyway, but we are really close to that. So you can even go back to my Audio Mass Survival spreadsheet, put in 100 hertz, and it'll tell me half wavelength, and that is 5.65 feet. So these two subs at 100 hertz are meeting at this point in space with a half wavelength offset, and they're also meeting here at a half wavelength offset, and that's why we get it. And the lower we go in frequency, the less ripples we're going to get, but deeper valleys. And if we go way up, let's go to 200 hertz, it's going to be even tighter pattern that starts to break apart. So it's more obvious and different in the audience if it's at a lower frequency, because you can walk it and hear it go up and down a little bit more smoothly. But anyway, that's what's happening with your subs. We have to pull them apart. So we can do things to mitigate that, to help steer subarrays and do cardioid or end-fire, whatever, which is outside the scope of this video today. But at least want to illustrate the basics of phase, how that affects subwoofer spacing, and make you aware that we're going to do a deep dive of this in my upcoming course, Making Sense of Sound. Again, make sure and grab my audio math survival spreadsheet and start to get familiar with all these concepts. My name is Michael Curtis. Thank you so much for watching, and I will catch you next time.